Okay, it looks like we're about ready to go. We've got a pretty good number in here, and anybody that comes in late, I'll just continue to add to the class to say we get started. I got one more. Okay, so let's see what we got. Okay, this is AP1 Lab, and we are going, everything you need should be found in the eLearn content section for you. There is no textbook for this. The syllabus explains everything that we're going to go through. We have the lab is broken up into 4 segments. The first segment deals with the microscope and human tissues and the skin, and well as some concepts on mitosis and cell division, as well as movement of water across membranes. That's the first section. There's a number of slides that you'll have to be able to identify from the PowerPoints. And the whole first first unit on lab is really to get yourself familiar with human cells and tissues and what they look like and how the microscope works and things like that. Not that we're going to use a microscope in this since we're online, but at some point, hopefully, maybe if you get into micro, you will. Now, the second unit that we cover is going to be on bones. And there are 206 human bones and about 200 different structures on the bones that you'll have to be able to identify. And this is something that we take real serious because in healthcare, you have to be able to identify these different bones and know them by memory, particularly if you're going into pre-imaging. If you want to be a radiographer, you've got to be able to know your way around the structures of the body. Now, it's not as bad as it sounds. And I give you 4 weeks to get ready for the bone test. After the bone section, we then spend 3 weeks looking at human muscles. And there are about 60 muscles, which is a whole lot easier to learn than all the bones. And then the last test covers the central nervous system, where if we were in class, we would dissect brains and eyeballs, but here you just get to look at pictures of them being dissected. So, and we'll talk about the special senses, and we'll talk about the general senses and things like that. And that is everything we cover in lab. We have 4 exams, and 1 for each unit. The exams are given online. We use the lockdown browser for the exam. If you have a Chromebook, it will not work on the lockdown browser. You'll have to use one of the library computers to take your exam, or the Sevierville campus has in the library. I know as of yesterday, they had 15 laptops available for loan for the semester. So you may want to talk to them about that for your exams. Otherwise, if you have a Chromebook, find another computer. Don't go buy a computer if you can avoid it. You know, the Chromebooks work fine for everything except the lockdown browser. I don't know why they don't. So you'll need, if you have a Chromebook, you'll have to find a way to take your exam. So we have 4 exams. There's 400 points possible in the course. And so you want to score 90% or above to get an A in lab. There is no final exam. The exams are not cumulative. So when you take the first exam, that's the last time you'll ever see those questions and those types of pictures for this semester anyway. So you won't see them again. And you won't have to try to recall them for any other exam, because the exams don't accumulate. And let's see, what else? As I said, all the content is available in eLearn, all the PowerPoints, all the PDF files. There are some very good videos in there on parts of I think I left some of those in there. On parts of the body that you might want to look at, like some on the skull. They're all very short, but they might be useful. And I encourage you to, if you are on the Sevierville campus, to come upstairs to the lab. Lab is in the lecture classroom, are the same classroom as room 217 upstairs, and I'm going to start putting out models of bones and muscles and tissue parts and things like that, so that you can come in and get a box of bones and take them out when we move into the bone section in a couple of weeks. Take them out into the classroom and sit down and work through them, or take them out into the hall, because there's no better way to learn parts than by playing with the specimens. All we have are models, but that's better than nothing. So if you are going to be on campus, on the Sevierville campus, the classroom 217, if it isn't open, then ask someone in the office to open it for you, or the campus police, or any faculty member that's around. I want to make sure that everybody knows that you all can come in. I would ask you that after you've worked with specimens, to spray a little disinfectant on it and wipe them down before you put them away. Other than that, feel free. And let's see. There is also a skeleton available for review down in the Tutor Center. Jennifer has a skeleton down there that you can take out and look at too. So, and that's when we get into the section on the bones. Now, as far as the first lab exam goes, there is a very comprehensive study guide in the eLearn content section. It's the only one that has a study guide, because everything else is just lists of things you need to memorize. Let's see, a couple of things on about the class itself. We have a schedule. We have a very tight schedule to follow. Unlike lecture, where I don't know when I'm going to get to a certain topic area in time for the. I don't schedule the exams and lecture because I don't know when we're going to get done with the lecture content. So, but lab is different. Lab is very concise, and I have set dates. Like this week is all going to be the first half of tissues and microscopes lab. Next week is the second half of it. And then we have a test coming up after that. So lab schedule is very specific. The lab schedule is found in your eLearn content under lab schedule. So you can go in there and take a look at it to know what we're doing each week. Now, as far as the exams go, since the exams are online, the way I want to do the exams will be the way I do the lecture exams. I will, once we finish the content area, I'll open up the exam and leave it open for 10 days. You'll have an hour to take the exam with only 50 questions. And then in the meantime, when we meet for lab again, so if we, when we finish up Unit 1 next week, then the following week, we would start Unit 2 on bones, even though the lab exam is open. So, I give you plenty of time to prepare for that exam. It's not like, okay, we're done, exams tomorrow. So one of the advantages of doing it this way, by having everything online, is we have a little more time to spend on topics in lab. It also means we're going to get done fairly early this year. I'm pretty confident that we will be done with lab, barring anything unusual, before Thanksgiving, which is really phenomenal. But that's my plan anyways, to have everything done before Thanksgiving. So we won't have lab the last 2 weeks of classes if everything goes like I have it planned. We also don't have lab during fall break week, and that'll be the second week of October, I think, because it's too hard to try and keep labs. Once we go off schedule, it's very difficult to try and maintain a split schedule. So I don't even try. And even though I know we're not on ground, it still makes it difficult to try and keep track of everything. Anyway, grading scale, I told you that. Don't have to talk about fire drills or anything like that, or dress codes. Anybody have any questions on anything on lab? Okay, I will say, and what is what I told everybody earlier in the week, that lab is not, the lab grade is not nearly as critical as the lecture grade. No one evaluates anybody going into any of the healthcare programs based on their lab grade. The only contribution the lab grade makes to your ability to get into a program is it's worth 1 credit hour, and it contributes to your GPA, which is just one of the components used to assess you for admission. Your lecture grade has a whole lot more impact than the lab grade does. So if you're in a situation where you're between what should I put more emphasis on, my lab grade or my lecture grade, an A in lab is not going to make up for a B in lecture. I'll just tell you that. Got to get that better grade in lecture. You know, if you have to sacrifice lab and take a C in lab, C's not going to, in lab's not going to hurt you. Because an A in lecture is going to be much more valuable, much more valuable. And I know what I'm speaking of because I have all the information, like from the nursing program, on exactly how they evaluate their applicants. So I know exactly how they take their points. So if anybody's curious and wants to know how they do it, you know, I can arrange to have a meeting on the Sevierville campus. It's no secret at all. But you know, there's always a lot of miscommunication floating around about that. So, having said all that, let me go into this first week's worth of information. Now, I should have it set up here. This, and here we go. Now, you all should see a slide that says week 1 lab, compound microscope, and the cell. And if you don't see it, I'm sure you'll let me know right away. So let me get into this. Okay, we're going to talk a little bit about microscopes today. You may have used a microscope in the past, and that's great because you've had some experience. And I wish we had the chance to actually use these in person, and maybe in another semester we will, who knows. But the microscope we have is a compound light microscope. We have no electron microscope here. We have no phase contrast technology here. We have a simple light microscope. It works very well for our needs. The nicer ones that we have are what you would expect to see in a working laboratory setting, for example. The compound microscope is called that because it has the ability to have a series of objective lenses and an ocular. So you can change the magnification that you want to use. Early microscopes had had a lens and an eyepiece, and whatever magnification you had with that was what you were stuck with. So if you wanted to look at something under a higher magnification, you had to use a different microscope. But our microscopes allow us to select between 40 magnifications and 1,000 magnifications. And so we call them compound because we have a series of lenses stacked on one another. Now, the objective lens is the lens that sits closest to the microscope slide. The objective lens magnifies the image, and then the eyepiece, which has a lens inside that also, the ocular, the thing you look through, also magnifies the image. So you have a double magnification here. So the objective lens may have a number on the side of it that says 4x, which means it magnifies the image 4 times. The eyepiece has a number that says 10x, and that magnifies the image 10 times. So if you combine the two, if you have a 4x objective and a 10x ocular, and you will always have a 10x ocular, you magnify the object 40 times. If it says 10 on the objective lens and 10 on the ocular, you're magnifying it 100 times. Now, the compound microscope works by light. We have a light source in the base of the microscope. And while that seems like a very common thing, it wasn't that long ago, maybe in the past 40 years or 50 years, that microscopes had mirrors at the bottom. And you would shine a light onto the mirror and the mirror would shine up into the microscope. It was also not unusual for microscopes, even 40 or 50 years ago, to point straight up and down. And the only way that you could look at something under the microscope was to stand over it and look down into the into the eyepiece. Yeah. Now microscopes have the viewing tube is at an angle and has a built-in light source. I've never seen a microscope, never used a microscope. It wasn't like that. But you can, there are still places around where microscopes like that, I doubt if they're in use, but they're certainly probably still available. Nothing wrong with them. It's not as convenient. So we have a built-in light source. We have a structure that is an iris diaphragm in front of the light source. It works like the pupil of our eye does. It regulates the amount of light coming in. A lot of times, we don't need to have a bright light at full intensity shining on the object we're looking at. Sometimes we want to dim it down, and the iris diaphragm can do that. Now, generally, we'll have 4 objective lenses on our microscope. The objective lenses are on a structure known as a nose piece. The nose piece rotates around. The 4 lenses are the scanning lens, which has a red band on it to identify it, and it has 4X stamped into the metal on the side of it. These objective lenses screw into the nose piece, so we can switch them out as needed. So the scanning lens only has a 4X. The low power lens has a 10X stamped on the side. The high power lens has a 40. It says 43. It had a 40. And the 4th lens that we don't use in A&P, but when you take microbiology on the ground, you'll use the 4th lens. The 4th lens has a 100 stamped on the side of it, and that will give you a total magnification of 1,000 power or 1,000 magnifications. And that's called the oil immersion lens, because we actually have to place the lens itself into a drop of oil on top of the microscope slide. And so we can go from 40 magnifications to 100 to 400 to 1,000. As far as A&P classes go, we never need to go past 400 magnifications. It's only in microbiology, because at 1,000 magnifications, you can see bacteria. You can see bacteria, you can see the different types of bacteria, you can look at funguses. Can't see viruses. Viruses are too tiny, but you can see the bacteria that you're looking at in microbiology. Light comes up from the light source, and it will go through the specimen on the slide and then up into the objective lens. To make sure that light doesn't go all over the place as it's coming off the light source through the diaphragm, we have a little thing called a condenser. The condenser is like a little magnifying glass, and it focuses the light so that the light rays coming up from underneath shine directly into the objective lens. Otherwise, it would just be like, holding a light bulb in front of the lens and saying, hey, here, we want to get as much light as we can into the objective lens. So the condenser, which looks very much like a magnifying glass, focuses the light right there into the objective lens opening. We also can focus. We have 2 knobs for focusing. We have a coarse adjustment and we have a fine adjustment. Coarse adjustment works by moving the stage that the slide is on up or down. And we bring it in close or we move it further away till we bring it into focus. And then we have a fine adjustment knob, which on these illustrations is a separate knob off away from the coarse adjustment, But in most microscopes, the coarse adjustment knob is a large outer knob, and the inner knob is the fine adjustment knob. So this is what, these are older microscopes. These are pictures from the Morristown lab. They still work, but they're not, I always like to say that when I show these pictures, Sevierville always has better microscopes, at least in the A&P labs. The micro labs all have the same scopes. So, okay. This is the eyepiece or the ocular that you look through. It's always got a 10x or a 10 power magnification. This is known as the body tube. This brings the light rays up. They come up through the objective lens. They go into this prism, which bends the light rays and sends them up the body tube at an angle. Some unnamed inventor 50 years ago or 60 years ago came up with the idea of bending the tube off at an angle to make it more convenient to study specimens. Brilliant idea. I don't know why nobody had thought of that for 400 years, because for 400 years, people just stood over and looked straight down into the microscope. The prism is located in this little box right here. Now this structure is the nose piece. It revolves around the opening, ultimately leading to the body tube. The objective lenses screw into the nose piece. There's one of the objective lenses right now. On this one, it only has 3. It has a scanning power here in red. They have a low power with yellow markings and a high power under with blue markings. So this is the scanning power is 4x. The low power is 10x, and the high power is 40x. And if you combine the low power, you combine the magnification of the objective with the magnification of the ocular, you get your total strength. So 4x and 10x is going to give you a total magnification of 40. 10x and 10x gives you 100, and 10x and 40 gives you 400. There's your mechanical stage that you move up and down with the coarse adjustment and the fine adjustment. The coarse adjustment is pretty drastically. The fine adjustment brings it in just right for your own eyeballs. There's the coarse adjustment knob and the fine adjustment knob. As I said, most microscopes now have a large outer knob for coarse adjustment and a smaller inner knob for fine adjustment, instead of having extra knobs all over the place. But they both work by moving the stage up or down. Light source doesn't seem like a big thing, but it really is. The base, we ask you when you're carrying a microscope to put one hand under the base and one hand on the arm. That's this portion back in here, because if you carry it just by the arm, microscopes are reasonably heavy, and the tendency is to let your arm swing down. And I've seen people carry their microscopes swinging them as they walk, and the ocular is not screwed in, it's just loose because it has to rotate. The oculars have come flying out, and if the objective lens, for example, isn't screwed in properly, it goes flying out and things break. You know, nobody intends to break it, but things just happen. So we ask you that when you are in a class with a real microscope, you carry it with 2 hands. It's no big deal. And then the light switch. And while that is also, seems like, you know, why am I pointing that out to you? Because every microscope is going to have a different location for its light switch. In Sevierville, we've got 3 different types of microscopes in 3 different locations. One switch is in the back, one switch is on the side, and one switch is on the arm. You know, so it's not a big deal, but just to point out that we have, you know, if you've got 3 different types of microscopes, there's 3 different locations. This is the iris diaphragm here. There's a little lever that lets it slide back and forth to open and shut it. And again, it acts very much like the pupil of your eye that regulates the amount of light coming in. This is a close-up here of the stage. These clips here hold the microscope slide in place, and the slide goes across the stage. I've seen people take their slide and try to put it in vertically so that it sticks out this way, and then wonder why it's not working. If there's any possible way to put a microscope slide on a stage wrong, I've seen it, and it's okay. That's what we're here for, is to teach you how to use it. I wish we were actually doing this in person. Anyway, that's the mechanical stage, spring clips that hold the microscope slide in place. You can move the slide up and down by moving the stage up and down. And then these two knobs over here on the far side allow you to move the stage itself front to back or side to side. Most newer microscopes have those dials underneath the stage, so they're not in the way, but they still work. Force adjustment, fine adjustment, iris diaphragm. And here we're seeing this little structure here is the condenser, because there's the objective lens right there. There's the nose piece, and the condenser focuses light, so it moves through the slide right into the objective lens. That's the condenser. These knobs allow you to move the stage front to back, side to side. And so you can, instead of having to move the slide around, which was also something that was done 50 years ago, now you can just move the stage around and find what you're looking for. It makes life a whole lot easier when you're looking for particular types of cells or tissues. Mechanical stage. Another view of the stage from underneath. Again, there's the iris diaphragm there. You can actually see the opening for the lens right there. This is the 100, and this is the 40x lens, objective lens there. The 100x would have a white band on it. So, diaphragm. Now, having thrown all that at you, probably, I didn't really try to confuse you. This slide is very helpful for explaining everything I just said. The objective lenses magnify 4 times, 10 times, 40 times, or 100 times. That's the oil immersion lens. The eyepiece magnifies 10 times, always. So to get your total magnification, you always multiply the magnifying power of the ocular, which is always 10x, times the objective, which can be 4, 10, or 40. And that gives you your total magnification of 40, 100, or 400. So make sure, just make sure you know this page, because there will be questions about, a few questions about magnifying power. Not that it's a big deal, but I would like to be able to know that, so that when you get into microbiology and if you have Dr. Malik, you'll know what he's talking about when he talks about how to use the microscope. Now, something else we see, it's a term called resolving power. Resolving power is the ability to determine the space between two objects under the microscope. Now, things that we can't, that look like they're combined with our eye, can be seen differently under the microscope. This resolution allows you to distinctly see different, separate structures. Let me give you an example here. This is a letter E. It's upside down and backwards. Everything you see in the microscope is upside down and backwards, just like in a telescope. Good telescopes, good microscopes invert the image. That's what we're seeing. But the other thing about this letter E, this is a letter E that has been printed on a piece of paper on a laser printer. Now, when you look at that letter E on paper, first of all, it's right side up, and it's not reversed, but it's also sharp and crisp. But when you magnify it 100 times, suddenly you see all these little jagged edges here. This is what resolution does for you. Our eyeballs would look at a letter E and have it look like this, nice and crisp and straight, no edges and nice smooth edges and everything. The reality is that when that toner from the laser printer hits the paper, it splatters all over the place. You got to see what an inkjet printer does. I mean, it just lines and lines of ink everywhere. But we can't tell that. We look at it, our eyeballs are not good enough to have any kind of resolving power to see the separate lines, the separate splatter. To us, this looks like a nice straight line, but it's not. And in a microscope, we'll be able to see in slides, in cells, we'll be able to see structures that to us would just look like a straight line, an edge. We can see the different structures inside a cell that we couldn't possibly see any other way. So this is one of the more interesting phenomena. I mean, if you have a telescope and you take pictures of the moon, for example, when you print your pictures, you're going to have to turn them around and flip them, because the picture you're going to get, what you see through the telescope, is upside down and backwards. The moon is the opposite way. You have to turn it around. That's just what they do. In cells, it doesn't matter, because a cell is a three-dimensional object, and there really is no up or down, left or right in the cell. So now, something else to understand when you're looking at specimens is that most human specimen tissue is transparent, and it's pretty much the same color. Once we get below the surface of our skin, everything is identical. It's only the pigmentation of our skin that appears different to people. Underneath, the organs are all the same. They don't, you can't tell the difference, because there is no difference. The only variations in color we have underneath the skin is that our heart and liver are dark red, our skeletal muscles are red, and everything else is sort of like a light tan. Everything. Many of the tissues are practically transparent. So the only way we can look at a lot of tissues is to apply a dye to them, a stain, which the stain bends light rays and gives you more contrast. So you really can't see anything otherwise, because it's practically transparent. But a stain that gets absorbed by different areas on the cell allows those areas to suddenly become clear. So at this point, I would normally have you make a slide of your own cells. We call it a wet mount, and we would have toothpicks, and I would make some bad joke about how we spared no expense on the toothpicks. We bought Walmart's finest, and you would scrape the inside of your cheek with a toothpick and smear that onto a glass microscope slide. What you're doing is scraping off dead cells, and then you would apply a drop of methylene blue to it, and the cells would absorb the methylene blue, and it would look something like this. Human cheek cells look just like this. They're flat. They stain dark blue for the nucleus and light blue for the cytoplasm. You can't see the membrane, but you can see where it's located. Something else to point out is in the nucleus, every nucleus is exactly the same. Every nucleus contains all the DNA of the person that it came from. It's just that most of that DNA is turned off. Only the segments of being a cheek cell are turned on, but everything is there. Well, this is a prepared slide. Here's one from a student a couple of years ago, pre-COVID days, I guess. There's 2 or 3 cheek cells stained blue with a little methylene blue. And there's a nucleus there, and there's a nucleus in there. And this is all sorts of debris that comes out of our mouth. Here's another one, sort of out of focus, but not bad. A lot of cells, cells visible. They took the stain very nicely, and you can see the dark spot in the middle. So it's a very easy process. It's a real hands-on process, and that's unfortunate that we don't get to do this for a while. But given the fact that we have a pandemic, the idea of sticking toothpicks in your mouth and smearing them around and throwing them away would probably send people through the roof. I will say that even when we did this pre-COVID, the microscope slides and the toothpicks and anything associated with that went into our sharps box so that it could be destroyed later on. Okay, now that's the microscope. Let's take a look at some other tissues here. Let me get out of this and go to the next slide. Human tissues, epithelial tissues. Okay. So this. Open this. Oops, that didn't do anything. I guess it would help if I could share screen. So everybody should see the slide that says human tissue types epithelial. And the reason I'm talking about this, epithelial slides, the epithelial tissues, that's what we just looked at. The stuff that came out of our mouth, if we'd done a wet mound of cheek cells, those are epithelial cells. Why do we care about epithelial cells? Who cares about epithelial cells? Well, they're the cells that cover our body. They cover the outside of our body. They cover every opening inside our body. If the body is open to the outside, it's lined with epithelial cells. So like from our mouth to our anus, lined with epithelial cells. They make up our first line of defense against pathogenic infection. Now, a pathogen is a disease-causing organism. And that's really not right, because viruses aren't alive. They're not organisms, but they are disease-causing agents. We're talking bacteria and funguses and viruses. They are, let's call them disease-causing agents instead. They can't penetrate our skin. Our skin is waterproof, it's thick, it's covered with oil, believe it or not. It's covered with sweat, and the sweat has a lot of antibacterial properties, which at least keeps the bacteria away. And we have our own healthy bacteria living on our own skin, which functions to crowd out any pathogens that might try to get in. If you had pathogens on the surface of your desk, you put your hand down on it, nothing would happen. Those pathogens can't penetrate through the skin. And these are all epithelial cells, layers and layers and layers of epithelial cells protecting us from infection. Now, how do we get infected then? Well, it's simple. You touch your face, touch your eye, you rub your eye, you rub your nose, you rub your mouth, touch your mouth, you wipe your mouth, stick your finger in your ear for some reason. Or you drink after somebody, or somebody sneezes on you and you breathe in the mucus in the water droplets in the air, or someone is busy shedding viral particles and you inhale them. But we can't get through our skin. And if we can block the other routes of entry, we have a much better chance of remaining uninfected. So epithelial cells do a great job. We have a variety of epithelial cells that keep us safe. That's what their primary role is protection, at least on the surface of the skin it is. Um, but there are only 4 tissue types in the body. Epithelial is one of them. It's a very large contributor to our body. We have muscle cells, 3 different types of muscle cells. Connective tissue, does exactly what it sounds like. It holds things together and connects things. And there's about a half a dozen different types, more or less, of connective tissue. And then nervous tissue. There's only 2 types of nervous tissue. So let's take a look at these epithelial cells here. If you're an epithelial cell, you're in one of 2 categories. You're simple, where you're only 1 cell layer thick, or you're stratified, where you have multiple layers. If you had scraped your cheek cells out, you were scraping a stratified layer. Lining of our mouth has multiple layers of cells. The outer layers are dead. They've been pushed up from underneath. They're designed to wear away. They're designed as we eat and drink and talk. We are spewing out cells all the time or swallowing them because they're there to protect the living cells underneath. So we either have simple cells or stratified cells. Simple cells show up where we want to have movement across a cell membrane. 1 cell layer thick, the cells in our lungs, the alveoli, where gas exchange takes place, where air exchange takes place. Those alveoli, those little sacs where oxygen goes into our blood and CO2 comes out of our blood, are made up of cells that are 1 cell layer thick. They look exactly like what was scraped out of our cheek. They're only 1 cell layer thick because oxygen can go across 1 cell. Can't go very far thicker than that, but it can go across 1 cell easily. Anyway, we have 2 categories and we have 3 types. We have what are called squamous cells. They are sort of an irregular cell. Cheek cells are squamous cells. The cells in our lungs are squamous cells. They're very thin, they're flat. The nucleus actually sticks up in the middle of it, but the cell itself is fairly flat. We have cuboidal cells. They're called that because they're shaped like a cube. We find them usually only in our kidneys. They form the kidney tubules. We have the columnar cells. The columnar cells are shaped like columns. Columnar cells, we find them where we're going to have absorption and movement, like our small intestine is lined with millions and millions of columnar cells lining our gut to absorb nutrients. We also have 2 ringers. We have transitional epithelium. Find that in our urinary bladder, in our ureters, and in our urethra. We say it's transitional because when it's at rest, it looks like columnar cells, but when the bladder expands and fills up with urine, goes from something the size of a walnut, the size of a grapefruit, it looks like squamous cells. And then when the bladder empties, it shrinks back down to the size of a walnut, the cells look like columnar cells again. And then we have my personal favorite, the pseudostratified ciliated columnar epithelial cells. Pseudostratified, false stratification. They look like they're arrayed in layers, but they're not. They're a simple structure, 1 cell layer thick. They look like they're stratified, so we say it's pseudostratified. They're ciliated. They have little tiny hairs on one surface, and they are columnar cells. And what they do is we find those cells lining our airway, among other places. And they line our trachea. And the cilia are covered with mucus. And as we breathe in dust and dirt, it gets trapped in the mucus, and the cilia beat. And they beat in one direction. They move that mucus up from our airway up into our mouth, into our throat, into our mouth. We swallow it into our stomach and destroy it. We swallow about a pint a day of that mucus. Fortunately, we're not aware of it, but we do that every day. Okay, so these are simple squamous epithelial cells. Probably the most common type of cell in our body is the squamous cell. And the simple squamous cell, irregular in shape. That's what the cheek cells, while they were stratified squamous, because there were multiple layers, they're still squamous. They still have the same shape. These are cuboidal cells. These are kidney tubules. We're looking straight down into the kidneys tubules right now. These little cube-shaped structures here. You notice how these stained purple. On the other hand, these stained red. It all depends on the dye that's being used. There's different colored dyes. There's yellows, there's reds, there's blues, there's pinks, there's oranges, there's purples. There's a variety of stains. The stains, in fact, can often tell you what type of cell it is too. So there are certain white cells that only take a certain type of stain. There are certain bacteria that only take a certain type of stain. So you'll learn all about that kind of staining in micro. But these are cuboidal cells. These are kidney tubules that you're looking directly into. And these are a cube-shaped cell with a large nucleus. One cell layer thick, because what we have inside the kidney tubule, we want to get out. We want to get it back into our blood supply. These are simple columnar cells. This is part of the small intestine right here. These cells are shaped like columns. And not only that, we have these white structures here. These are known as goblet cells, and they generate mucus. In lecture, I've been talking about serous membrane and mucous membrane a little bit. We talked about, if you're in the lecture tomorrow, you'll hear all about it. The lecture today heard me talk about if you are an internal membrane, you are what's known as a serous membrane. If you're an external membrane, you are an epithelial membrane. And the difference is that if you're external, you make mucus. If you're internal, you make serous, but it's the same stuff. And it's the same cells. They're just called endothelial cells. Anyway, this is simple columnar epithelial. These white things are known as goblet cells, and they secrete mucus. We line our esophagus with goblet cells. We line our small intestine with goblet cells. We have goblet cells secreting mucus in our mouth. That's where the term mucous membrane comes from. We line our rectum and our anus with goblet cells. The uterus and the vagina are lined with mucous membrane. Epithelial cells, stratified squamous epithelial with lots of goblet cells for mucus in here. Mucus prevents friction, and our bodies don't like friction at all. If you think friction doesn't exist, rub your hands together real fast for a couple seconds. Just feel how it starts getting warm very quickly. That's friction. We don't like that. So we have layer upon layer of cells that are lubricated. We don't want any friction when we send nutrients through our small intestine either. That would hurt. We don't like pain. Another example here, a simple columnar cell lined up very nicely. Lots of goblet cells here secreting mucus to make the passage of nutrients, for example, go very easily. Simple columnar epithelial, again, goblet cell. Again, single layer. Now this is pseudostratified ciliated columnar epithelial, false stratification. These cells look like they're stratified. They look like there's multiple layers because it looks like there's multiple nuclei in here, but they're not. This is a single layer. These things up here, where the arrow is, are called the cilia. These are tiny hairs that will move in one direction and one direction, and they'll move forward and then slide back, move forward and slide back. And the mucus that gets released from these goblet cells, like there's one, there's one, there's one, will cover the cilia. And in the airway, as we breathe in dust and dirt and debris and particles and junk like that, it'll land here in the cilia, and we will push it up towards our throat, towards the opening to our esophagus. We'll swallow it and get rid of it. It keeps our lungs clean. The other place that we see cilia like that is in the female oviduct. The female oviduct is the tube that's also known as the fallopian tube or the uterine tube. Three different terms for it. Fallopian tube. The egg gets released from the ovary. It drifts into the fallopian tube. The fallopian tube is a 2-inch long tube. The only way that the egg can get to the uterus, whether it's fertilized or not, is for these cilia to push it along. There are some rhythmic contractions of smooth muscle around the oviduct, but primary boost is the cilia, and it moves fairly rapidly. It takes 7 days for that egg to go 2 inches. I guess that's rapid if you're an egg. Because remember, at this point, you are the size of the pointy end of a pin. So you're not very big. Even if you're fertilized and you're growing like crazy, you're still not going to be very big for a while. But consider this. In less than a month, you're going to be 1 inch long and have a full skeleton and a beating heart. More on that later. Okay, so this is what pseudostratified ciliatic columnar epithelial cells look like. There's the cilia. The cilia move in one direction. If they're lining the airway, they're moving mucus. If they're in the oviduct, the fallopian tube, they're going to help to push an egg along. There's the cilia right there. And this is what they look like up close. This is what you would see in the fallopian tube, the oviduct, or the uterine tube. The egg would be drifting along here, and the cilia would be pushing it along, generating a current for the egg to drift towards the uterus, drifting along towards the uterus. And that's how the egg gets there. And then when it enters the uterus, if it's been fertilized, it may or may not implant. There's no guarantee that a fertilized egg is going to implant itself. No guarantees at all. Doesn't matter how fast it's been growing. You know, by the time a fertilized egg gets to the uterus, it's well over 150 cells, and it's starting to take its shape. Because remember, in 3 weeks we'll have a heart. In 6 weeks we'll have a full skeleton in place, and we'll be about 1 inch long. So it doesn't matter how fast we're growing. If we didn't implant, nothing's going to happen. And you know, only about 20% of every fertilized egg implants. So anyway, but the cilia moves us along. The cilia, its other big role is this, is to move the egg along here in the female oviduct. This is transitional epithelium right here. Transitional epithelium is found in the urinary bladder, in the ureters, in the urethra. They look like columnar cells right now. When they stretch out, they look like squamous. They tend to be found only in a few locations, but so they appear to change their shape as they stretch out and appear to flatten out. So we call them transitional epithelium. And so they look like this. Here they look like columnar cells, but when they expand, as the bladder expands, they flatten out and they look like squamous because they're very stretchy. You know, the ureters, the bladder, and part of the urethra are going to have these transitional epithelial cells here, because the urinary bladder can go from holding about, about 50 mils maybe something the size of a little walnut to something to almost a liter, something that, you know, it'll expand its shape to almost the size of a grapefruit. So this is stratified squamous right here. This is what you would see lining your mouth. Multiple layers. We line our mouth with this, we line the rectum, we line the anus with it. Anywhere where we want to have, where we're going to have wear and tear in our bodies. Our skin is stratified squamous. Lining of the rectum and anus, lining the uterus and the vagina, lining the urethra, lining the esophagus, lining the inside of our mouth. Anywhere that we're going to have wear and tear. Some of those areas are going to be lubricated with lots of mucus. Some are going to be waterproof, like in the surface of the skin. A lot of them are going to be non-waterproof. We have a substance that waterproofs our skin called keratin, what we make our fingernails with too. We don't want to have our mucous membranes waterproof. We like them to be soft and squishy. So they're stratified, but they have no keratin. They have no waterproofing. We don't need that because that would make them rough and dry, like the surface of our skin. Can you imagine what it'd be like to swallow something in the esophagus and send it down the esophagus if it was passing through membrane that was as firm and rigid as the surface of our skin is, without any lubrication? That would be painful. So stratified squamous epithelial cells designed for protection, designed to wear away. The outer layers are dead. The inner layers are alive and are constantly pushing up. And so that's the role. This is what we see here in our esophagus. Stratified squamous right here. These outer layers are dead layers. The living layers are pushing up underneath. They are what we refer to as non-keratinized. The mouth, the anus, the esophagus, the vagina, the urethra are not keratinized. The skin is keratinized, making it waterproof and making it dry. That is epithelium. So okay, the other three tissue types I can go through fairly quickly here. Muscle, connective, and nervous tissue. There's only three types of muscle cells in our bodies. One type that we have control over, and the other two are involuntary. Connective tissue runs through includes things like blood and collagen fibers and bone and fat, and they're all a little different. And then we have nervous tissue. So muscle types, three types of muscles. Skeletal muscle, the stuff that we can control. Voluntary control. Raise your arm, lower your arm, walk, talk, move, chew, eat, swallow. All these things are under voluntary control. Skeletal muscle is also called striated because it has a series of stripes, light and dark bands. But we control its movement. Cardiac muscle is also striated. And that's its only similarity to skeletal muscle, because cardiac muscle is found only in the heart. Clever, because it's called cardiac muscle, but it's only found in the heart, whereas skeletal muscle connects all the arms and legs and fingers and toes and bones together. Cardiac muscle, involuntary control. And the heart functions like one great big giant muscle cell. Totally different than any other muscle does. Smooth muscle is also under involuntary control. It doesn't look anything like the first two. It's shaped like a spindle and doesn't have any striations at all, no stripes. It surrounds our blood vessels. It surrounds our digestive tract. It surrounds our esophagus from our mouth to our anus. It surrounds every artery and vein in our bodies. And again, it's totally involuntary. We have nothing to say about the expansion or contraction of our muscle cells around our digestive system or around our blood vessels. So this is skeletal muscle, highly striated, light and dark bands right here. Lots of nuclei in the muscle cells. Lots of striations, light and dark bands. They slide over top each other. We'll talk about that when we get into chapter 9. Lots of fat cells around for energy. And fat cells are a great source of energy, even better than carbohydrates. Multiple nuclei. The muscle cells have many nuclei per muscle cell, which is fine because muscle cells don't reproduce. Muscle cells don't regenerate. So you kill off a muscle cell, it stays gone. So we don't have to worry about the DNA. We don't make copies of muscle cells, so there's no problem here. When muscle cells were forming in utero, they were formed as many individual cells that fused together. That's why they kept the nuclei. We don't know exactly why, but they did. Anyway, the nucleus doesn't affect anything because the cells aren't gonna, at least as far as growth goes, because the cells aren't gonna reproduce. They're gonna grow. You can enlarge your muscle cells by exercising and eating lots of protein, but you can't make new ones. This is smooth muscle, shaped like spindles around our blood vessels, around our digestive system. Smooth muscle has one nucleus per cell. No stripes, no striations, totally different than what skeletal muscle. Again, we have no control over our smooth muscle. You know, consider this, it's a hot day outside right now. You go outside and the smooth muscles around the blood vessels leading to your skin are going to relax and increase the blood flow to your skin to radiate more body heat. If it were 30 degrees outside and you went outside, the blood vessels to your skin, the smooth muscle around those blood vessels would start squeezing them, reducing the flow to the skin so that we wouldn't lose as much body heat from the surface of our skin. And we have no say in that. We have no control over that at all. The same with moving food through our digestive system. If you had a sandwich for lunch, if you had a burger or whatever you had for lunch, it's being pushed through your digestive system by squeezing the digestive tract. Squeeze and relax, squeeze and relax. And we have no say in that. It doesn't automatically. Involuntary control. More smooth muscle there. Make sure you remember this slide because lots of people get this slide and that stratified squamous slide mixed up. Smooth muscle again. More smooth muscle. One nucleus per cell, long and skinny cells. This is where we see smooth muscle a lot. This is our digestive tract. This is the wall of the small intestine. And right here are layers of muscle. These are smooth muscle layers here. This is the outer covering of the small intestine here. And these are the smooth muscle layers surrounding it that squeeze food and waste products through our digestive tract. Smooth muscle right there. Cardiac muscle cells are unique. They branch. They branch into other cells. And they're very definitely striated. They usually only have one nucleus per cell. But they branch at a structure known as an intercalated disc. Nobody else has these discs except cardiac muscle cells. And the disc has openings in there so that the cells can communicate to all the other cells. And what this does is this allows an electrical impulse to travel through the heart so that the entire heart contracts at one time. Every cell in the heart contracts together with the same strength. It isn't like an arm muscle where in your arm, only the cells that are stimulated are going to contract. In the heart, every cell contracts. So whereas like in your biceps muscle, for example, only the muscle cells that you want to use are going to contract to pick up a cup or to write something down or whatever you're doing with it. But in the heart, every cell contracts, and every cell contracts with the exact same force. So we communicate that signal to every cell in the heart so they all respond at the same time with the same force. And the amazing thing is we do that every 7/10 of a second for 80, 90, 100 years. Okay. Again, this is what it looks like. We see the striations, but we also see the branchings. There's a branching there, branching. See, look at the branching there. These dark lines are the intercalated discs. Sometimes they're difficult to find. Sometimes you have to sort of imagine it and see them like maybe that's a disc and that's a disc. These are very easy to spot over here though. Anyway, cardiac muscle, striations, intercalated disc. The disc has gaps in them that allow the electrical signals to pass through rapidly. Branching fibers there. And then these are the individual nuclei there. Now the next topic, connective tissue. This isn't going to take very long. Connective tissue. These are cells that have, this tissue has 3 criteria. It has to be living cells in a matrix that can either be a solid, a liquid, or a gel with fibers of some type. They can be elastic fibers, they can be structural fibers, they can be fibers in solution, but they're fibers. So anything that meets the criteria of living cells in a matrix, can be a solid matrix like bone, with fibers. So, fiber types that we encounter, collagen fibers, among others. Collagen fibers are incredibly strong. Collagen is the most abundant protein in the body. Collagen is what we use to make tendons that attach muscles to bones. They are incredibly strong. Collagen, a strand of collagen is equivalent to a strand of stainless steel. It's that strong. Elastic fibers are exactly what they sound like. They're made of elastin and they're stretchable. And then the third type of fiber are the reticular fibers. They form this mesh that holds everything in place. You ever wonder why the organs in the abdominal cavity don't go sagging down and drop down to the bottom of the pelvis? Why are they, we always see them arrayed with the liver here and the stomach here and the small intestine wrapped around by the large intestine. Nothing's falling apart. Well, they're held in place by the reticular fibers. Collagen, organized in a parallel structure, side by side by side by side. You have great tensile strength here. Incredible strength on this. Collagen is so strong that when it forms a tendon, the tendon will usually snap the bone. When it's stretched to the point of breaking, the tendon will snap the bone before the tendon breaks. So it is actually, in many places, it's stronger than the bone that it's holding on to. Elastic fibers can stretch out and then rebound to their original shape. We find them in around the arteries. You ever have your pulse taken? That's an example of elastic fibers. There are elastic fibers in the walls of the arteries. And every time a surge of blood goes through, the fiber, the artery wall expands out and then snaps back. And that snapping back is the pulse. It's different from the heartbeat. It's equivalent to the heartbeat as far as monitoring the same thing, but it is different. The pulse is the snapping back of these elastic fibers. Our vocal cords are elastic. They stretch and rebound as we make noises with our mouth. Our sound, volume, intensity, pitch, tone, all that stuff is based on our vocal cords and their ability to stretch. The trachea is elastic. The bronchi are elastic. Our skin is elastic. It doesn't rip and tear when we move around. Our ears are elastic. Reticular fibers, as I said, form this mesh that holds things together. Our spleen, which is a very squishy organ, and so is the liver, an extremely squishy organ, is held in its shape by the reticular fibers. What do these connective tissues look like? Well, this is what's known as loose connective tissue. This is a lot of our packing material in our bodies. This is like the styrofoam peanuts that goes into a packing box that protects everything and holds things together. It's made of reticular fibers, and it's made of elastic fibers, and it's made of collagen fibers. And it has a lot of cells in here called fibroblasts, which produce cells known as fibrocytes. A lot of times those fibrocytes end up becoming scar tissue. But when we're using it as loose connective tissue in the body, we're using them to help hold things together. Fibroblast, elastic fiber, reticular fiber. Can you tell the difference? I can't tell the difference. I only know what they are because they're labeled. These fibers all look the same. But the whole structure is known as a loose connective tissue because there's lots of fibers in here, lots and lots of fibers. And of course, there are the cell nuclei, and somewhere in here, the reticulars. And then, of course, there's collagen in there for strength, too. Loose connective tissue is woven together with all three types of fibers. It's holding things together. It also holds epithelial cells to their basement membrane. Keeps them from sliding off. Dense connective tissue, we see that in our tendons and our ligaments. The Achilles tendon, the largest tendon in the body, attaches to the calf muscle and attaches to our heel. Is a very powerful tendon, and it does probably more work than any other tendon does in our bodies. It's the exception to the rule that when stretched to the point of breaking, it will snap the bone because the Achilles tendon will wear out. In some people, because we have people tear their Achilles tendon all the time. The tendons attach all bones and muscles together. Muscles don't attach directly to bones; they attach indirectly through tendons. And so a muscle pulls on a tendon, which pulls on a bone, and we get to amplify the strength there too. But again, since the tendons are all collagen, they will usually snap bone before they snap themselves. And this is what it looks like. This is collagen fibers woven together. Don't get this mixed up with the stratified squamous cells or the smooth muscle cells. But this is what, imagine, if you will, one thread. You have a spool of thread, and you try to pick up a 10-pound weight with one thread, or a 100-pound weight with one thread. Try to pick it up and tie it around, try to pick it up, it's going to snap the string. But suppose you have 1,000 of them, 1,000 threads, all lined up together, just like this, in a big group, all tied at the same spot. You're going to be able to pick that 100-pound weight up with those 1,000 threads because they're going to be working together and amplifying their strength, just like the weave that we see here. Dense connective tissue, great strength in pulling in one direction. And tendons attach bones to muscles to bones. Very, very strong. Very little elasticity here. The cells that are present are fibroblasts. Irregular connective tissue is where you have more elastic fibers, and here this has an irregular arrangement. We find this when we see a joint capsule, like in the area around the shoulder, where we have the scapula and the clavicle and the head of the humerus all coming together. So we would cover these joints with this flexible tissue that can move in any direction. Cartilage. Cartilage is a white, waxy type of substance. We have cartilage in our nose, in our ears. Our trachea is made of cartilage. Our skeleton at 6 weeks after conception was entirely cartilage, and that became the framework and the model for bone. So it is very flexible. It's got great strength. It's made up of chondrocytes. So they are, anytime you have the ending CYTE, that means a cell. So the chondrocytes are embedded in this matrix of a gel. It's like putting bananas in Jello. So you have bananas floating in the Jello. Bananas are still bananas, and Jello is still the Jello, but the bananas are intact. The slices are still intact inside the Jello. Well, that's what happens here. The cartilage cells are embedded inside their matrix. It looks something like this. This is hyaline cartilage right here. This is the stuff in our nose. This is the stuff that lines the surface of our joints at our bones. This is the stuff that makes up our airway. This is what our skeleton was like when we were 6 weeks after conception. Not 6 weeks old, but 6 weeks after conception. These cells inside here are called chondrocytes. So they are chondrocytes. They are living, well, they were living cells. They were living cartilage cells. Anytime you have site, means cell. They're trapped in a bubble called the lacunae. When they were functioning as a chondroblast, a builder, anytime you have blast means builder. So as a chondroblast, they were laying down the matrix. They were laying down the gel that they were, the chondrin they were going to be living in, the white waxy stuff. Well, at some point, they realized that they had trapped, the chondroblast realized they had trapped themselves in this bubble. And so they became a chondrocyte, a living cell. Now, only problem with cartilage is cartilage doesn't have a good blood supply. No blood vessels connect to it. They depend on diffusion, the movement of nutrients and gases to work their way through the gel and get to the cells, and then have the waste products work their way out. That's why cartilage injuries take so long to heal. They don't have good blood supply. Bone's different. Bone also has a matrix. The bone matrix is even harder. It's made of calcium and phosphorus. It's mineralized. It's a crystal, but it has lacunae with living cells in there. We have osteoblasts, bone builders. Osteo is the prefix for bone, just like chondro is for cartilage. Osteo is for bone. Osteoblasts lay down the bony matrix. And once they trap themselves in a bubble, the bubble is called the lacunae. And then we have the osteocytes inside the lacunae. But what's different is that these lines here all are all canals that connect. And in a bone, all these living cells in their lacunae can communicate to other bone cells. So bone is a very definite living tissue with lots of living bone cells in there, and getting their nutrients and their oxygen and getting rid of their waste through vessels and nervous tissue that comes up and down through these canals. And then they connect through all these little tiny canals to every one of these lacunae, to every bone cell. Bones regenerate, bones recover quickly from injuries, bones respond very quickly. Osteoblasts lay down the matrix. Osteocytes live within the matrix in these lacunae. And it's wrapped with fibers, collagen fibers. That meets the definition. It's wrapped with collagen fibers, so bone is extraordinarily strong. It resists compression greater than steel. Adipose tissue, loose connective tissue, it stores fat, lots of elastic fibers, living cells in a matrix. It's a gel-like matrix, and that's the fat. And it is surrounded by elastic fibers. It isn't the adipose tissue. It is the fat that gets stored in the adipose tissue. So here we have, there's a nucleus right there for a cell. And there's probably another nucleus there, and one there, and probably one there. And these are the adipose tissues that have elastic fibers there. And then the last type is blood. Blood is a connective tissue because it has living cells, red cells, white cells, and platelets in a matrix of salt water, that's the plasma, with fibers. The fibers are in solution. The fibers only become present when we have a cut and we have to clot. So we meet the definition. It sounds really strange, but we meet the definition. Living cells in a matrix with fibers. Blood cells there's a white cell, there's a white cell. These are red cells. The little purple things are platelets. They are floating in the plasma. The fibers are invisible, but they are in solution, and they will form when they become activated to form a blood clot. It's a platelet, which is really just a cell fragment. But the red cells and the white cells are the living cells. Well, the red cells, of course, don't have a nucleus. Red cells don't reproduce, but white cells can replicate. So, the last category of tissues is nervous tissue. Only two types. This big thing is a neuron. Neurons send signal down this structure called the axon. That's how they communicate. Neurons communicate to other neurons through their axon. Information only goes one way. These little purple things, there's the neuron cell line. These little purple things are called glial cells. There's about 10 times more glial cells than there are neurons in the body. There's a lot of neurons. There's even more glial cells. The glial cells do all the support work. They do all the protecting and cleaning up and making sure that the neuron gets fed and taking out a damaged nerve, a neuron. So they do all this work so the neuron can focus only on sending nerve impulses. There's the nucleus. Neurons don't regenerate. We have all the neurons we're ever going to have when we're born. Yes, we don't get new ones, just like muscle cells. We don't get new muscle cells. And if a neuron is damaged, it stays damaged. It probably is taken out by these glial cells. Now, in some neurons, if it's only the axon that's damaged, the axon can be repaired. Because if we couldn't repair the axon, how could we possibly do any kind of transplanting? How could we reattach injured limbs? if we couldn't repair the axon, if the axons couldn't get repaired. They have nothing to do with it. They repair themselves. But if it's only the axon, then many neurons can repair themselves. Okay. Now, this is a enlarged view of that small intestine I showed you earlier with the smooth muscle up in here. This shows you the cross-section of the small intestine. The outer layer is the serous layer. If you haven't heard this in the lecture yet, this is a good time to hear it now. Since the small intestine is open to the outside in this portion down in here, but not open to the outside, this is open to the abdominal cavity. While they are the same type of cells that you have here and here, this is called serous membrane. This is mucous membrane. Same cells, just location. Look at all the goblet cells that are present here to lubricate. Underneath that, we have the smooth muscle layers. We have two layers, a longitudinal layer and a circular layer, running in two different directions. So they can squeeze from two different ways to force food through the digestive tract. There's the longitudinal layer, and there is the circular layer there. Moving further in, we have the submucosal layer and the mucus layer, because now we're open to the outside. This is a mucus layer here, and we have lots of goblet cells, little purple stained things in the goblet cells. And these are all the simple columnar cells, simple columnar epithelium. They're now in mucus layer territory, not serous layer. Same fluid, same type of cells, different names, different locations. Because this is the lumen of the small intestine, which is open to the outside. Now our skin, this last layer, this is a cross section of our skin. Again, epithelial cells right up here, dead cells on the surface, living cells underneath. The epidermis is mostly dead cells. It isn't until we get to the basement layer of the epidermis that we run into living cells. The dermis is all living tissue, and underneath the dermis, we have the hypodermis. Our basement layer, our connective tissue, our loose connective tissue layer is underneath the epithelial cells. So our basement layer is right along in here, holding the epithelial layer to the dermis. This is a better illustration of it. Here's our, what we call the stratum corneum, the outer layer, the waterproof keratinized layer. Here, this is the epidermis here, the dermis here, and the hypodermis here. Most of our fat shows up in the dermis, in the hypodermis. The epidermis is where the dead layer, and the dermis is where we start seeing blood vessels show up. Receptors for touch, pressure, and pain are located in the dermis. There's a hair follicle right there, an oil gland to lubricate our hair follicles, keep them from getting brittle and stay flexible. Also to help lubricate our skin. This is a sweat gland down here with an opening called a pore right here. Adipose tissue there. Now, moving on. The stratum corneum, dead tissue, waterproof, protecting us. This clear layer is called the stratum lucidum. Below that, we have the stratum granulosum, stratum spinosum, and we move down to the basement layer here, where we have that layer of connective tissue attaching the epidermis to the dermis. So this is the stratum basal here. This is a Pacinian corpuscle. It is a deep pressure receptor. There's our sweat gland right there. we release water through there to cool us down. There's the opening of the pore. This is the erector pili muscle. This is what causes us to have goosebumps when we get cold. We raise our hair follicle in place so that we can trap air around the surface of our skin to stay warm. That's why we get goosebumps. Believe it or not, it helps a little bit. We probably don't notice it that much, but the goosebumps are there to try and maintain a thin layer of air over our skin to try and warm up, trying to stay warm. Oil glands, again, for lubricating our hair. There's the hair follicle with the hair shaft inside of it. The hair shaft, I'll tell you, there is no such thing as gray hair. When a hair loses its pigment, it turns transparent. And when the hairs around it, you know, when you have a few that are transparent and other hairs around that are not transparent, the light rays are bent, and so the hair looks gray, but it's actually transparent, as you can tell it. It isn't until every hair loses its pigmentation that they look white. You know, and even then, they're really transparent. So, but there's so many of them together that they look white. There's no such thing as white hair, it's transparent hair. So, and there's no such thing as gray hair. It's simply a distortion by light caused by some hairs losing pigment and others not. And of course, there's our, excuse me, hair root. And again, the model of the skin. The only thing I want to show you on this are these ridges here. I want to get down past this and show you these ridges. Okay. These ridges here, I like this because it's three-dimensional. These are called the dermal papillae. The dermal papillae are our fingerprints. These are the loops and the whorls and the lines that we see in the ends of our fingers. And they're caused by these raised ridges that push up into the epidermal layer here. They're at the connection between the dermis and the epidermis there. This is the stratum basal right here. And those are our fingerprints right there, the dermal papillae. And that is, I think, everything I want to show you on that. And we're done with everything on Unit 1. So it wasn't that painful, I hope. So, okay, so that covers everything that was in Unit 1, the integumentary system, all the human tissues, and the parts of the microscope. Next week, we'll come back and finish up Unit 1, and then we'll open up the test and leave the test, and we'll talk more about that next week. Anybody have any questions?
Will we just be labeling the test or the pictures for the test?
Well, there'll be a lot of that. There'll be a lot of identification on the test. You know, there'll be a few questions. Now, there is a very good study guide that I've put together for Test 1. And that's, you can find that in eLearn at the end of the table of contents section. It lists everything that you would have to know, I think, I hope, I'll have to go back and take a look, but I think it's a pretty good study guide. It's the only study guide that you're going to need for the semester, because in muscles, it's just a list of the muscles. You have to be able to identify the muscles. Bones, you have to be able to identify the bones and the bone parts. So, you know, I've never figured out how you would have a study guide for when you're just looking at lists. You know, so if I can put together one, I will. So, but anyway, yeah. Okay. Okay, and that's all I've got. Anybody have any other questions? Okay, then I'm going to wrap this up and get us out of here. And if I haven't had you in lecture yet, I'll see you tomorrow.